Okay. Hi everybody. Um, I thought that I would do a tutorial on how to use Bambi because I get the question a lot, and I think it's helpful to show an example. So, I'm going to show an example of how you can run Bambi using the data that you can download, um, that's open access, and I'll give you the citation for that. And I will show you how to do this on a Mac computer, but it's all the same on Windows. Okay, sorry, that's awkward. So I will share my screen. So, um, Bambi is, of course, a bedform analysis code that you can get from GitHub. Let me just search it for from my account. Julia Morphology. If you just search GitHub Julia Morphology, you'll find it. You'll also find this link here that says Tools, Julia Cisneros Geoscience. It's on my website. I'll click both to show you those. So here, this is my website. That BAMBI stands for the Bedform Analysis Method for Bathymetric Information. This is the link to the GitHub for BAMBI, but I also on here have a link to Toolbox's other bedform analysis methods from other colleagues, and it's all linked here on this uh, link for MARID, Marine and River Dune Dynamics Research Group. So we have Bambi here. We have a couple of other bedform analysis methods um, from other groups for different methods and different reasons. And if you're interested in that, you can check out a comparison of these different methods um, from Leon Schreiber, JGR paper recently published, I think 2022, 2021. I can put that in the description if that's helpful, and I can put this link in there as well. Um, but there's tons of different methods and all very valuable, all very useful for their own reasons. And the paper that Leon has led explains that a little bit more. But the one I'll share with you is the one that I've made, which is Bambi. The database that Leon shares also has example um, multi-beam data sets or bathymetry data sets that you can use to practice. But I'll just share with you the one that I use, which is the Paranod data set, multi-beam data from Dan Parsons' work, Parsons et al. 2005. So this is what it looks like when you open Bambi, GitHub, Bambi. Um, all of the codes are here and a little bit of a README. There are like four major functions of Bambi. Well, more than that. There's Bambi, the main function, bedform threshold, which is a function within Bambi, fine wavelength, another function within it, keep, which is a function written by David Yang, slope calc, a function within Bambi as well, run from Excel, and then a parameter file Excel sheet, which I can explain how to use. The output from Bambi are measurements of dunes, their morphology, their height, wavelength, lee side angles, and the flow depth that they exist in. Um, for for all dunes in the dune field, separated by scale, which is based on a statistical threshold, but you can change that. You don't have to change that. It depends on if you have different scales, but for now, we're going to just keep it with this threshold separation, which separates what we call large dunes and small dunes. And this is assuming that you're working in a river, but Bambi is scale indiscriminate, so it works across a range of different scales. It can work on things like flume data as well. So that's also important. So what you're going to do is you're going to download Bambi. You can click here, code, open with GitHub Desktop if you use that, or download as a zip file. Um, I would recommend that if you don't use GitHub, and um, you can run it single for just one data set, which I'll show today, and then you can run it for like a bunch of data sets if you have like temporal repeat surveys or something. And I'll explain how to do that as well. So when you download it, I recommend putting it in your documents folder. So it's in my GitHub folder, as you can see. So I'll bring this to the front. And what you're going to get is you're going to get all of the functions here, and then this parameter file here. And so when you look at that in MATLAB, it's a MATLAB code. I apologize, working on getting something for Python. If you open BAMBI, which is what you're going to want to work on dominantly here, is you're going to see this part here, add path, gen path. You want to add your MATLAB file or folder path for all of your base functions. But you don't have to do that because the base functions that you need, well, yeah, just do it. It's helpful. So add your link here for your MATLAB, change that, and then you're going to change this link here to link to wherever your BAMBI folder is as well. You can see that there are all of the different um, all of these sections, and I can, if that's helpful for somebody, I can help you. I can talk you through that, but it's not valuable for right now because I'm just showing you how to run BAMBI. I'm sorry, I have way too many functions open. So what you're going to do is you're going to find the data set that you want. And for this example, we're going to use the Paranal multibeam data set from Parsons 2005. So this is, let me search that paper really quick. This is Dan Parsons' work. I'm a fan of Google Scholar. So this is Dan Parsons' 2005 paper where he has created this beautiful multi-beam data set of the Paranal that you've probably seen on um, tons of different things, including a book cover that some of you may be familiar with. This is available. Dan's made it open to people. I think if there's a link down here to get it, I'm not sure, but I do know that it's available through other routes. For example, Leon Schreiber's paper has a link to the data, I believe. I don't know. If you need the data, you can ask me and we can figure it out, or Dan would probably be happy to help figure it out as well. Anyway, you go in, you have the data. Sorry, this is a little crazy. I thought I had it in here, but I don't. So you have this ASCII file, and this is important. You want a lot of multi-beam data will be downloaded like XYZ points, and then when you upload it into a GIS or something, you'll have to grid it. And it's already gridded to whatever the resolution is that you want. But the reason that we need it in ASCII is because you'll see BAMBI relies and leverages on image analysis. And so the ASCII file, if you open it up as a text file, it looks like this. So you can see we have headers. We have 1, 2, 3, 4, 5, 6 lines of headers. And then we have this big matrix, which is essentially just a big image of each cell value, what the Z value is at that location, like what the bathymetry is or elevation, if you're going to be working with elevation. And so that's why we need the ASCII file. So that's, if you don't have that, that's the one thing you'll have to do is you'll have to translate your bathymetry data into some sort of ASCII file. If it's experimental data, you can kind of create your own coordinate system. The nice thing about if you're working with real data, it's already georeferenced, and so it's already going to have these headers made. If you're working with like lines or grids from XYZ grids from lab data, you have to play around with it and just create like your own coordinate system where, this is 0, 0, and then this is just the number of columns and rows of your matrix or something, or of your grid. So that's something to consider. So you'll have this ASCII file, and if you open this ASCII file, it's a bathymetry grid. And what you're going to do is Bambi will read that ASCII file. It goes through a series of steps. It rotates the grid. It runs through each line. It identifies Dawson-Lee side slopes. And then it measures all of the values of, the height of the dune, the lee side angles of the dunes. Um, it rotates everything back, and then it runs this bed form threshold. I'm being very vague here. We can talk about it in detail if you want. It runs this bed form threshold. So the bed form threshold here looks at all the heights of the dunes that have been measured from this data set. And I'm saying dunes. I'm being like really vague and all-encompassing. I mean bed forms, but I'm just referring to Paranal dunes in this case. Um, but it looks at all the dunes and it does a quick, histogram fit, looks at, uses a gamma distribution to define the mean and the standard deviation of that data, and it defines the threshold as the mean plus the standard deviation. And it says anything that's greater than the threshold is a large dune, and anything that's smaller than that threshold is a small dune. Now, in the Paranal, this works really well because there are two scales of bed forms. There's small bed forms climbing over large bed forms. If you have a case where you don't think superimposition is occurring, then maybe you don't need this threshold. And so what you can do is you can change this and you can say threshold is 0, right? Or maybe you say, actually, my data is a little rough. It's a little dirty. It's a little, we all have real data is not always beautiful. And maybe you say, actually, I know that anything that's less than like 10 centimeters is an outlier or, whatever you want, whatever your definition of that is. And you can say 0.1. And then what that will do is it'll say, okay, anything that's greater than 0.1 height, dune height, is a large dune. Anything less is a small dune. And then in your head, I'm just ignoring the small dune data because that's all artifacts, right? So that's kind of where you can play with the code. I recommend just sitting here with the threshold and mean plus standard deviation at first, because it works well. It's based on, the statistics of the system, and it seems to work well. It's based on the gamma distribution and the work from others who show that the gamma distribution is a good representative of bed form characteristics. So that's why we chose it. So yes, you do that. And then you'll see in Bambi that we have fine wavelength. So fine wavelength, once we've separated all the large and the small dunes, we separate them into two different grids, and we know where their locations are. And so what fine wavelength does is it goes back and it looks at, okay, I have a dune here and I have a dune here located. It locates the troughs of the dunes. And then it says, okay, the space between this point and this point is this dune's wavelength. And so the reason fine wavelength happens after the scale separation is because if we did it before, then we would have a lot of really small wavelengths representing a large dune, because it's looking at the nearest trough, which could be the trough of a smaller dune that's climbing over it. So that's why fine wavelength happens after, and that's generally what this part of the code does. After that, we go through both of the grids, the small and the large dune grids, and we save all of the data. We save the X location, the Y location, the height, the mean lee side angle, the maximum lee side angle, the wavelength, and the depth. The slope direction is supposed to show you where the direction of the slope that the lee side is facing. It works sometimes it doesn't. I think if you want to use it, we can talk about it and we can look at your data and see how valuable it would be. It really depends um, on the resolution of your data and how finicky it is to like those little bitty variations in aspect. The cool thing about the large dunes is that it also tells you the flow depth, but it shows you what the location of the steepest slope on the dune lee side, which is really great. And in my paper, you can see how that's being used. The data saves in a folder that is located where the ASCII file is. And it saves it in a folder called data tables, and it saves a small dunes text file and a large dunes text file. And these are both um, tables with all of this data, X, Y, X location, Y location, height, etc. All right, so that's how we do it. So if we're going to run BAMBI, what we do is we will run the functions. Yeah, we'll run the functions, small dunes, large dunes equals BAMBI. We're going to pull the file name here. We're going to see the flow direction. Okay, so flow direction of BAMBI in BAMBI means the direction that the flow is pointing towards in azimuthal coordinates. Now I know that Paranod data points um, down like towards the southwest, and so that's around like 200, 220 um, degrees. But I'll show you how we do that. So this is the Paranod data. And what I'm going to do is I'm going to measure the bearing, and I'm going to, oh, maybe not the bearing, maybe the angle. Okay, so that is negative 60. Okay. Ah, all right. Well, I thought I knew how to use the angle. Anyway, we know that north is 90, and we know that or north is 0, east is 90, south is 180. So this is pointing, maybe let's say 30 degrees off of 180. So we'll say that the flow direction here, it's going from um, it's going from the top to the bottom. As you can see, we're going down, and we can see that the dunes, the lee sides are facing down this way. So we know that it's going down towards the southwest. So we can say that the flow direction is like somewhere around like 210 degrees. It doesn't have to be perfect. You can be perfect, but for this case, I'm not going to be. So we have to have the flow direction, right? So we're going to put 210 degrees for azimuth coordinates. Flow var. Flow var is automatically 40 degrees. That's just the threshold that it uses to define what is a lee and a stoss side. I recommend sticking with that for now. And then 1 for export. So we're going to run this, and it's going to take a second. I'm going to pause this and let it run. Okay, so BAMBI ran, and it ran for like 10 minutes or something, not crazy. And now we have the output of the data set. You can see already that I forgot to suppress the function. So it already gave me a lot of data, but we can go in and we can look at the within the folder that the ASCII file is that we ran. You can see here there's a new file or folder called data files. And within here we have large dunes and small dunes. So I will go ahead and open the large dunes that we don't really want to see. We just want this one. So you can see here we have the large dunes text file, and it's comma delimited, and it has X, Y, the dune height, the mean wavelength, max wavelength, that slope direction, flow depth, and um, or sorry, mean least side angle, max least side angle, flow depth direction, slope direction, flow depth, and location of the maximum dune height. And so these are the outputs. So for large dunes and then small dunes will look the same. It's just a table. It's a text file with all these outputs where each row is a dune measurement. And so if we were to using like something like QGIS, if we were to open this, let me see if I can just throw it in. Yeah, I can't. I have to open it. So if I were to open this in any GIS software, you can see I'll just choose this example here. I'm going to stop sharing for a second so I can open it up. So if I just open up that example to look at what the data looks like. Okay, I'll start sharing again. All right, so here I am in that folder, YouTube tutorial folder, data tables, and I'm going to just look at the large dunes export file. And we'll call this large dunes. That's fine, the layer name. I have that custom delimiters, comma, it's reading. And then in here, like in any GIS software, you're going to tell it what field is the X, what field is the Y. And then usually I'll do the Z field as like field 3, which reports the dune height. And I do that so that I can look at the information and see what that value is. But you can change that to anything, whatever value you're interested in. The coordinate system, that's a great question. I didn't think about, let's just see if it's the same coordinates. It's not. So this isn't correct, but I'm just gonna tell it a coordinate system because it's in UTM. And that probably wasn't the best idea because, yeah, let me stop and I'll put it in the right coordinate systems. I'm gonna pause this. All right, sorry. This is what I get for not actually having everything ready to go. So in the GIS system, we have the Paraná data here. And again, if we were to like run it across just a simple profile tool, you can see that this is a dune. And what you can see is on this profile, I'm kind of hovering over where the trough point is right here. And what you can see is, if I can hold it at the same location there, it's kind of hard. What you can see is that these points here are where the trough is of this dune, for example. And if we go forward, or here, let's go backward, you can see there's a dune. If we go over here, like that trough point, there's points right there that have the dune. And so that's because BAMBI saves the data at the trough point of the dune it's measuring. And then if we zoom in, you can see that they look like lines, but when you actually zoom in, they are points and they're spaced like at the resolution of the data at minimum, so 0.5 meter resolution. And that's because BAMBI splits the grid into these into columns as it's running through profiles. And so a quick check that I like to do just to make sure that it's measuring the dunes the way that I want it to and that I'm comfortable with the measurement is I'll do a quick profile and I'll look at the height. So this is -5 at the crest, at the top of that dune, and -6.7. What was it? -6.7 and 5. So it's like 1.7 dune height. And so then I'll pick the measurement there. That's not what I wanted. Let me find another one so I can make sure I'm doing the right thing. Okay, so if I'm looking at this dune, this one is 5.1 and 6.7. So again, it's like 1.6. And so what I'm going to do is I'm going to pick a measurement there that looks at the dune height. And the reason that it's not clicking is because I'm not on the right layer. There we go. So if I look at the what that point is, just the values of that point, you have the X and the Y, and then you have this value, right? Field 3, which is 1.56, about 1.6 meters. And that is reporting the dune height. And so I'm really comfortable with that because that's what I measure just if I was looking at by eye and measuring by hand over here, right? So if I measure here, it's 5.1, and here it's like 6.7, so 1.57, 1.6, around there. And so that's kind of like a little bit of a check, and there's a lot of other things you can do, but that kind of lets me know that, it's one, I can see visually that it's picking out the dunes, but two, like the measurements are making sense to me. Some things to consider are, something like this. This is sort of like a bedrock outcrop. And so, anything that's being measured over here in this area is probably not real because it's measuring just the topographic difference of this bedrock area. So in the future, if you're processing this data, you might want to cut that out, and you could just cut it out and let it be a blank, like masked blank space, and Bambi will just kind of move through that and not consider it. And so, you can think about if you want to do that before or after. But I usually like to do it before. Like I'll cut this area out because it's just bedrock, and then I'll cut maybe this part too because that's also bedrock. And that way I don't have to do any post-processing. And I know that the statistics in the threshold that are used to define small and large are not relying on measurements that are coming from this, which are not real, which are not dunes at least. So that's kind of like a real quick run through of how to run Bambi and what the outputs are. You can see that for each one, you get all of those measurements, heights, least side angles, wavelengths, all of these things. And so you could, look at everything spatially. You can, change this. For example, maybe you want to look at um, graduated and you want to color them by the dune height. And you can say, okay. And for some reason, that's not. Oh, it's because the size is wrong. The symbol needs to be bigger and the color, and I need to add classes. That's what the problem is. Why? Okay. And so you can see like now I'm visualizing all these points by the height of the dune. And you can see we have high dunes here, like at the apex of their dunes, and then on the edges, sometimes we have lower heights. And you could do a lot of those kinds of spatial investigations, but you can also look at, what is the distribution of dune heights for the entire area, for the center of the channel, for the left sides of the channel. What are the least side angle distributions? What are the wavelength distributions? How do they change spatially? You can do that in GIS, or you can do some fun like spatial averaging and other kinds of spatial analyses through coding. So there's lots that you can do. But this is just a quick example using a really, really beautiful and very clean data set to show you what these outputs look like. Small dunes, if you were to throw that file in here, you would see a bunch of small points, and you would see that they're actually measuring all of these little superimposed dunes that are climbing over the larger dune. So that's another thing that you could think about. And and if that's something you're interested in, I'd be happy to talk more about it as well. But this is just a quick little overview of how to run Bambi and how I kind of pull it into GIS, check it, do all those fun things. So thank you so much. I hope this is helpful. I'm sorry that it was very all over the place. I should have planned it better, but I just thought I'd do this quick run through. It could be helpful. All right. Great. Thanks for listening. Contact me if you have questions or need help. Bye. Okay, before I forgot, because I totally forgot, I want to show how to do the batch runs, the run from Excel using a parameter file. So I'm going to go ahead and share my screen again. So I just showed how to run Bambi, how to run it with the Paranal data that we have. And I want to show how to do the Excel, how to run for batch. So I'm going to share my screen again. I'm going to walk through this. So we ran Bambi, yay, fun, amazing. I'm going to look at what you would get if you downloaded the Bambi from GitHub. You can see here we have the Bambi threshold, all the scripts, but here we have a parameter file XLSX. It's an Excel file, sorry. And I share this as an example. And so what I'm going to do is I'm going to show this the in the folder so that I can open it. Cool. And this is just a default example, right? And so what this is it's a table with DEM file in the first column, flow, flow var, and export, which are all of the inputs needed for the Bambi function. And here you can see that we have rows, and each row is a file name, a flow, a flow var, and an export. So what you're going to do is if you're running a batch, so say you have like temporal data, and you want to run each one of them, but you don't want to do what I showed you in the script, which I don't recommend, like, retyping each one, resaving it into a new location. You want to run them in batch. This is a good way to do that. So what you would do, I'm just going to go ahead and save this I'm going to save a copy actually. So yeah, I'll save a copy. And I'm going to go to the YouTube tutorial example. I'm going to save it in here as a parameter file. Okay, so I saved a copy. Now I'm going to delete all of this, and I'm going to delete all of these because I don't actually need to go and do multiple. But what I'm going to do is I don't have in this example the bat. I don't have multiple like a temporal um repeat or something. I do, but I'm not gonna spend the time to look for that. But instead, what I'm gonna do is I am going to this is really funny. I'm gonna say I'm gonna make a new folder, batch test. I'm gonna copy this ASCII file into here, and I'm actually gonna copy it again, and I'm gonna name it not copy. I'm gonna name it 2. So I have 2 in here now in my batch test. And I just copied them because just for the sake of this example. But this could be like a survey during time 1, a survey at time 2. Or, you have a large area and for computational efficiency, you want to cut it into smaller areas. So you have this large area and you have subset area 1, area 2, area 3, area 4. And so you put all of those ASCIIs in one folder, and you would instead of um, running them separately, you put them all here. So I have that one here, and I'm going to make sure that I don't have the quotations there. And I'm going to put the next one here. And for some reason, it always gives me that little quotation thing. I don't know why it does that. Cool. I want to look at this really quick to make sure. So I'm just making sure that I don't have to put the quotations. I always forget to tell it it's a string. Yeah, there's no string here. It's just the path name. It has no string things. Sorry, it's the end of the day. I'm tired. My brain's kind of dead. So I have those here, right? And this is 2005 and this is 2005 too. It's just a copy of it, but you can imagine it's something different. And I'm going to put my flow directions, which I think was 210. I don't remember. It's fine if it's not. Flow var is 40, export is 1. So it's going to export. And I'm going to save this, right? And this is the parameter file that is saved within the batch test folder. Now, the cool thing is if you go into the run from Excel here, all you have to do is you have to tell it where this parameter file is. So if I open up this here, the parameter file is right here within my YouTube tutorial uh, folder. And I have batch test ASCII files here. So I'm going to copy the path name of this parameter file, which has the locations of those ASCII grids that I copied. And I'm going to put it here in the top where it says parameter file. So I'm telling the script where this new parameter file is located. It's located in the YouTube tutorial folder. And in this case, all you have to do is just run the script. You don't have to do anything else. You don't have to do all of the command window stuff. Just run the script. And when it's run from Excel, it says analyzing one, which is analyzing the first file, and so on and so forth. And so I'm going to stop sharing. I'm going to pause this while we go through this process. But as you can see, it's already moving through pretty fast. All right, y'all. So it's getting late. I'm tired. Maybe I'll edit this in the future. But I didn't want to wait until the code ran for 30 minutes because that's how my day's been. So I terminated it. But I'm just going to explain how this works because, yeah. So yeah, because I don't want to wait for it to run. So um, when this runs, it will run through each one of them, and then it saves the data as large dunes, small dunes inside at the location of the ASCII file. And so since we are pulling the ASCII file from here, you could imagine that there would be a folder here with that same name and a folder with this same name. And within those folders, the exports, the outputs, large dunes, small dunes would be in those folders instead. So I'm going to find an example of like my data output so that you can see it. Because I don't want to have to wait for this to run. I'd rather finish this video and then go home. As you can see from my screen, it's like 4:57. So I'm tired. So I'm gonna stop sharing for a second and I'll just find an example. I'm being so open with my data and organization. Oh, what a nightmare to share the brain, my inside my brain, aka my files and folders and organization. Um, so let's look at this one. So I'm going to show her a folder of some of my um, a data a data set that I ran in batch. So I'm going to share my screen again, and I'll walk you through it. So in this case, this area was really big, and I knew that I wanted to um, separate it for computational efficiency. So I cropped them and I put them in a folder called crop sections for Bambi. And I literally cropped them area 1, area 2, area 3. And so initially all I had in this folder were these ASCII files. Area 1, area 2, area 3, ASCII. And what I did, and you can see that in the parameter file here. I can open that actually, that might be helpful. So I have them all in here, area 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With the flow variations, it's a river that changes direction, so the flows are different. Flow variation is the same, and export is the same. It's all exported. And so after I ran this on Bambi, Bambi saved all the data in this way as a folder. So the data from area 1 is saved in an area 1 folder. And then within that folder, I have the large dunes and the small dunes folder. Same for area 2, large dunes and small dunes folder. Now, for this, it's a little bit helpful because since the flow variations can change, Run from Excel exports and saves the file with the flow angle and the variation angle. So you can see this one is 20 degrees. So the river was pointing like in this direction, whereas in the area one, it's 330. So it was pointing in the opposite. So it was kind of, so it's, it's a river that's bending. And that's just me telling you that so that you know what those numbers are. But really, it's the large dunes and the small dunes folder. So this is what it would look like when you export, when you run from Excel. This is kind of the data, the structure of how it would be organized in the folder that all of your ASCII files are in. So I hope that helps. I'm sorry, I just didn't want to wait for Karanal River, so I figured I'd share a different example. Um, I hope that helps. Let me know if you have questions. Please reach out to me. You can reach me on my email. Um, Super happy to chat about it. Hope this helps. I'm sorry I feel like I'm very scattered. I've recorded this video at three different times of the day, just when I had like 30 minutes here and there. So I'm sorry if it maybe as you're watching it, it feels like very disconnected. That's probably because it is. And you've probably seen the slow demise of my brain throughout the day, um, which I'm sure is very entertaining. So thank you all so much. Hope this is helpful. Have a good day. Yay. Yay, Bambi. All right. Bye bye.